Board. All right. So, yeah, I got honorable mention at USFO. My team won the Bibalashvili Award at USA YPT. It's like this physics research competition. And I qualified for a CSEF, which is like a research competition thing. I know a bit of physics, and outside of physics, I do basketball and I like running. All right, next slide. Then let's do some icebreakers. So we'll go through everybody. How about everyone say where you're from, like your state or country, right? And then what's your favorite field in physics? It's okay if it's just mechanics or you don't have a favorite field. No judging, right? And also, what's your favorite food? Because everyone likes food, right? Yeah. So how about let's start with AD. Uh, yeah, do you want to like unmute and
Yeah.
like
So I'm from like Texas. I guess if I had to pick, I'd choose like quantum physics and then food. Oh no, I have no clue.
all right, nice. Quantum physics is very cool. I don't really understand it. I don't think anyone understands it, but like, yeah, that's nice. What about uh Arkishman? I don't know if I'm saying your name correctly. Correct me if I'm wrong. Yeah,
I'm from Ohio. Favorite field in physics is probably thermodynamics and probably bread.
all right, nice. Okay, so how about Arya and you go next?
I'm from Texas. I don't have a favorite field of physics, and my favorite food is pizza.
All right, nice. I like pizza too. Okay, Avi, how about you go next?
I'm from Texas. My favorite field in physics is probably thermo, and my favorite food is pasta.
Nice. I don't know why. There seem to be a lot of Texas people here, but I mean that's
Yeah.
pretty yeah. Okay, how about Daniel, you go next. Uh wait, Daniel, are you there? Uh wait, Daniel, I don't think I think you're mute right now. Wait, let me ask you to mute.
Can you hear me now?
Oh yeah, I hear we hear you now. Yeah, yeah. So yeah. Well, where are you from? What's your favorite field in physics and what's your favorite food?
Um, I am from Spain, and my favorite field in physics are electro electrodynamics.
Nice. That's funny.
And
Yeah.
my favorite food, fried chicken.
Nice, nice. That's funny because actually yesterday I came back from Spain. I was on vacation there. I must say Spain is really nice. So your country is really nice and yeah, it's great to meet you. So how about
Mhm.
next yeah. Next let's have Da Wei. You want to
I'm
go?
from
What?
Texas, and my favorite field is thermal, and my favorite food is pasta.
Nice. All right. How about Gabriel? You go next. Okay, you don't have a microphone. Okay, he's from the Philippines. He likes quantum physics and oh, he doesn't like food, but all right, that's fine. Oh, you love all food. Okay, that's good. That's good. Yeah, I also love all food. That's good. Okay. Yeah. All right, Josh, how will you go next?
Hi, my name's Joshua. I'm from the US, and I guess my favorite field in physics would be plasma physics, and my favorite food would be uh, pancakes, I guess.
Nice. Pancakes are good. All right, Kevin, how about you go next?
Hi, I'm from Australia. I haven't really done enough physics to really say what my favorite physics field is, but my favorite food is oatmeal, and I'm currently eating that as well. It's in the morning right now, so I'm pretty sleepy.
Oh, nice, nice. Oh, Australia seems really nice. Do you see a lot of kangaroos there?
I guess, but not a lot. Only if you go in like the regional areas.
Oh, that's pretty cool. Yeah, Australia seems pretty nice. Um, okay, let's move on to Lawrence.
Yeah. Hello? Yeah. I'm from the US. My favorite field is probably optics. My favorite food is strawberries.
Nice, nice. All right. Miruna, do you want to go next?
Hi, my name is Bruna. I'm from Romania. My favorite field is probably thermodynamics, and my favorite food is peanut butter and jelly sandwiches.
Wow, nice, nice. Wait, Romania is a beautiful country. I wish I could go there someday. Yeah, that's really cool. And how about next let's do Nawin. Am I saying your name correctly? Oh, okay. Nguyen lives in Germany, likes quantum physics and sushi. Nice. Yeah, sushi's really good. Okay. It's unfortunate that we can't hear you, but yeah, that's all right. How about Nerver? Do you want to go next?
Uh, I'm from New York. My favorite field in physics is fluid mechanics, and my favorite food is apples.
Nice. Yeah, apples are good. All right, Ryan, do you want to go next? Ryan, you there? Oh,
Oh, oh
yeah.
yeah. But can you hear me?
Oh, yeah, yeah, we can hear you now.
Oh, okay. I'm from Washington State and I like mechanics and my favorite food is udon.
Oh, yeah, udon's so good. Wait, do you like udon or so you like udon more than ramen, right?
Yeah, yeah. I
Oh,
like the big noodles, you know?
yeah, yeah, yeah. Big noodle's good. Yeah, yeah. Okay. How about Sanji? We go next. Oh, um, okay. Sanji lives in California. Also likes quantum physics. Oh, doesn't really have a favorite food. A lot of you guys love quantum physics. That's really amazing because it's a very difficult field. But yeah, that's cool. Sarah, how about you go next? Oh, okay. Sarah lives in New York and likes mechanics. Nice. I also like mechanics. Um, okay, Shamik, how about you go next? I guess Shamik is not there. Oh, Shamik is here. Okay. Okay, Shamik lives in California and likes astrophysics. Wait, Shamik, what's your favorite food? No favorite food. Oh, okay. All right. Okay, Sing, how about you go next? Oh, Sing likes electromagnetism. Favorite food is pasta from California. Nice, nice. How about Skiru? You want to go next? Oh, yeah, Skiru is from Bangladesh, likes astrophysics and quantum, loves all food. All right, that's good. All right, finally, last but not least, Sudeep, you want to go next?
Sure. I'm in California. I like me basically only done mechanics. Uh, I like pizza.
Okay, that's good. That's good. All right. I think we're done with all the icebreakers now. Uh, I don't think I skipped anyone, but yeah. So let's move on to some content. All right, here's gonna be our class structure. classes will start by reviewing the homework. Today, there's obviously no homework because it's the first class, right? But basically, like 1 or 2 days after each class, so like a day or two, like tomorrow or the day after tomorrow, I'm gonna be sending out an email containing like the slides and the lecture recording for like those who couldn't come or you want to like review the recording. And I'll also send out the homework for the class, right? So homework, it's assigned every week. It's not mandatory, but try to look at all the problems and do what you can, right? Like you're gonna like the only way to get better at physics is to do some problems. And like that's basically just doing the homework. I'm like selecting problems for you that I think you'll benefit from, and then like you can gain insights and like grow your mental picture, right? It's gonna benefit you if you do the homework. And my recommendation for how long you should spend on each homework, probably spend like a good hour on every week on the homework, right? Because like spend a good hour, make sure it's a concentrated hour. Like don't be like doing the problems while watching like YouTube or something, right? Just like focus on the problems for an hour, and then that's all I ask from you, and that's good, right? And then if you have any questions about the homework, what I recommend you guys to do is to go in our Discord server, and then in the in the channel, or yeah, I think it's called a channel, right? The channel for this class, the summer 2025 advanced mechanics class. It would be great if you could like type in your question and send it in the chat. And I want everyone from the class to contribute to like, reply to that, add on your suggestions, add on your feedback, add on like other questions you have. So it will be like a collaborative nature, right? Because physics is also about collaboration, and like research, that's also collaboration, right? So I want you guys to collaborate on all the problems you do, including the homework. Class will be mainly lecturing, but we'll also do a lot of problem solving too, to like, show the concepts, because you can't just listen to me doing the problems. You also have to do the problems yourself, right? So you can actually like when I'm not there, or like your other physics teacher is not there and you're doing like an exam, then you're actually able to do the problems on your own, right? That's the end goal, right? All right, another thing about class, videos must be on at all times. If you don't have a working camera, that's okay. You don't have to message me about it. I'll just go by an honor system. Um, yeah, so just if you can keep your video on, it helps us like interact better, and we'll stay connected, and I'll be able to like judge from your facial expressions whether I'm going too fast or too slow. And by the way, if you think I'm going too fast or I'm going too slow, or you have like a question about something I said, like just you can just unmute and interrupt me and yell out. I won't get offended, don't worry. Or if you don't want to like unmute and tell me, you can also message in the chat, like send a message to me in the Zoom chat, and I'll do my best to respond to it. But yeah, the most important thing here is to ask questions whenever like you don't understand anything, because like we're gonna be building up on materials. So if you don't understand stuff now, it'll be harder to understand stuff later. Um, but yeah, like the goal of this course, like we want to be able to master the F equals MA, or whatever the mechanics competition is in your country, and basically do USFO level uh problems in mechanics. That's the goal, right? All right, let's go on. All right, here's our course syllabus. It's 4 weeks long. Today we'll be talking about statics. Next week, dynamics. Next week, oscillations and rotations, and next week, more rotations plus gravitation. If you want to look at the full syllabus, I've attached a link in the slides. So like, tomorrow or the day after tomorrow, when I send out these slides, you can like click that link and check out the full syllabus. It's like much more detailed. It covers like specific topics we're covering each class. And that way, before each class, you can maybe like do some research on topics we're going to cover, or look at the like basically read on the material in whatever textbook you use, and that way you'll be more prepared. And as always, make sure you join our Discord server. It's that link over there. Reason why you should join our Discord server, one, it's a place for you to like collaborate with your classmates on homework or if you have any physics questions in general. It's also a really like it's a much easier way of communicating than doing an email, right? Of course, if you have questions, you can always email us, but like the preferred method of communication is through Discord. And also you'll get like important announcements about our classes and also like other opportunities outside of Paragon X. You'll get information about it in our Discord. So I really recommend you guys to join our Discord server. That way you'll be like kept up to date about everything, right? All right, and then today's class, the goal of today's class will be to build your intuition about basically statics problems and learning neat tricks when solving those problems. So we'll be doing a lot of problem solving. Now you can build up your like mental toolbox, right? And then you'll become a really good problem solver when it comes to problems about statics. That was a lot of talking, so let's actually do some physics now. So first, let's review a bit, right? Today we're talking about statics, so we're first have to talk about forces and torques. Forces, you probably like know already what it is. There's a reason why you're in this class, right? Just like F equals ma, you should know that, right? Now torque, you guys, it's a bit more complicated, right? And there are a few misconceptions about it. And the first main misconception that a lot of people have is that it's like people think you take torque about a certain axis. And that's not a correct, that's not the correct way of thinking about it. Torque is taken about a point, not an axis. So for example, if I have maybe like, let me draw, say I have a body over here, and then maybe I have this origin over here, and then say I apply a force in that direction, right? That's my force. Now, torque, right? What does torque mean, right? Torque, it gives us a change in angular momentum, so it causes angular acceleration. In other words, it causes the change in the angular velocity of the object, right? So what's the exact definition of torque if I know the force and the point at which I'm taking the torque about? Well, okay, if O is the point I'm taking the torque about, and I know this point P is where the force is applied, then I have this radius vector over here. I'll call it R. It's pointing from the point P to point O, okay? So R equals vector PO, right? R vector. And then we'll define, this is the torque. So it's the F vector crosses the R vector. And notice you have to be very particular about the direction of R. It's not, R is not OP, okay? So this is not equal to vector OP. It's equal to vector PO. And you might be thinking, okay, how do I remember this definition? And you also might think that maybe online you've seen another way of writing is torque equals R cross F. Are these two equivalent? In a way, yes, and in a way, no. They both are supposed to mean the same thing. So what is different between these two definitions is the definition on the radius vector. You'll use this definition if R equals to OP, but you'll use this if R equals to PO. And how do I really memorize that? Well, think about it this way. So if I have a disk over here, and let's say it's like three-dimensional, right? So let's say, actually, let me clear the board up a bit so it'll be easier to see. All right, so let me draw in red. If you have a disk over here, this is our disk. Oh, whatever, it's in blue. But it's a disk, and then this is our rotational axis, right? And there's going to be like, say it's rotating in that direction. So it's rotating, if you look from top, it's rotating counterclockwise. Now, if my force points, say I apply a force in that direction to the right, that's my force. Now, I want my, now you know, torque is like dl over dt, which is like IA, right? If you're applying a force in that direction, you're causing an angular acceleration that points, it points in the upward direction. Basically, it's making that force is making the disc rotate in that direction. So it's making it rotate counterclockwise. And if you remember, if you want to use cross products and you want to find the direction, you use the right-hand rule, right? So remember, you take your fingers, like your second to fifth fingers, you point them in the direction of the F vector. Well, if we're using this definition, right? You use your fingers, you point it in the direction of the F vector. In this case, it's pointing to the right, right? And then I want to curl my fingers in the direction of the R vector. Someone tell me what the R vector is in this case. Nerverd, can you tell me, or can you draw, let me know if you can draw on the board. Can you draw on the board where is the R vector when I'm doing the F cross R?
Isn't it pointing upwards?
Wait, can you draw on the board? Yeah. Are you able to draw on?
I don't know how to, sorry.
Wait, do you see on your bottom left corner of the screen, is there like a little green pencil?
No.
No? Oh, okay, that's all right. Well, oh, you guys can't draw. Yeah, I don't really see any setting to let you guys draw, but all right. Basically, all right, so we want the cross product to point, basically we want the cross product to point in this, we want this to be our F cross R, right? The upwards direction. So if we know that F is towards the right, what direction do we want the R vector to be? So remember, if for the right-hand rule is you take your, yeah, towards the middle. Sudi said towards the middle. Good job. So we want our R vector to be in this direction. Let me use a different color. So this is the direction of our R vector. So that way, if we take our four fingers, well, like second to fifth fingers, you point it in the direction of F, which is towards the right, and you curl them in the direction of the radius vector, and my thumb is now pointing upwards. Remember the right-hand rule, right? If you have two vectors, you're doing the cross product, you can get the direction using the right-hand rule. So if you forget the definition of like what torque is, like whether it's R cross F or F cross R, you can use this method to find like which one it is, right? Based on the definition of R. So like basically in summary, if that was like a bit complicated or like that was a bit confusing, just make sure that if your R vector is pointing from the point at which the force is applied to the point at which you're doing torque about. So the radius vector points from the point where the force is acting to the point where we are calculating the torque about, then your torque is F crosses R, okay? Just remember that, and you should be good. Let me erase all this.
But I have a question.
Yeah, what's up?
Wait, does it actually matter which one we use? Like, is it more useful if we use F cross R versus R cross F?
Actually, it really doesn't matter which one you use. As long as you keep a good mental picture, like just think of one and just stick to it, right? Because like there's no really like benefit of using one or the other, but when you're using one, you really have to be sure on what's the definition of the R vector. Like, does it point from the point where the force is acting to the point where we're calculating the torque about, or the other way around? Because if you have two, remember, you have two vectors, V and U, you're doing, if you're doing V cross U, right? That's equal to the negative of U cross V. So in the end, like, just make sure, like it doesn't really matter which one you use, just make sure you keep a clear mental picture of what's your definition of the R, and you should be fine. Does that make sense? Yeah, all right, okay. That's great.
Can I ask a question?
Yeah, what's up?
Is there like a specific point we should take the fixed point to be
Oh yeah,
usually?
that's a good question. Yeah. Which point you're taking the torque about? Well, actually, you can take the torque about any point. Like it doesn't really matter which point you're taking the torque about. Different points you take the torque about, they may or may not lead to different torques. We'll talk about that in a bit later, but basically you can choose whatever point you're taking the torque about. Does that make sense?
Yeah, okay.
All right, yeah.
So it
All right.
didn't have to be the center in that diagram,
Yeah, it can
basically.
be any point. Yeah. Yeah, you can choose.
Okay.
Yeah, yeah. Um, does anyone have other questions? I really like these questions. Yeah. All right, I guess there are no if you guys well, let me see there. Yeah, there aren't any questions in the chat, so let's keep going then. By the way, if you have any questions, just shout it out and then I'll do my best to respond, right? Yeah, asking questions is always a good thing. Right, so now we've reviewed torque, right? So remember, torque is F cross R. Just remember, or R cross F, right? Just remember what's your definition of the R. And remember, once we're doing dynamics, you're going to need to know this. Torque is the derivative of the angular momentum with respect to time, also equals to the moment of inertia times angular acceleration. Don't worry if you're not really clear on that. You can review about it after class because we're gonna be covering it next week, not this week. So you'll be fine for this week. Let's go on to the next slide. All right. Definition of a static system. All right. If a system is static, the net external force and torque on the system must be zero. So it's under equilibrium. So if I translate this into mathematical terms, for the net external force is equal to zero, this condition, what that means is just if I'm summing all of the forces, the vector sum of all the forces must equal to zero. And the net torque on the system must be equal to zero. So that's just, I'm doing this sigma of Fi crosses the Ri. And remember, Ri is the radius vector from the point you're taking from the point the force acts to the point you're taking the torque about. And the point you're taking the torque about, or like that fixed point, you can choose any point in space to do a torque about. It doesn't really matter which point you do it about. But for the system to be static, this must be equal to zero. And we'll see later that it doesn't matter which point you're taking the torque about okay, let me say it again, in a different way. If you have a static system, it would not matter which point you're taking the torque about. It would always be equal to zero. We'll show a proof of that later, but for now, just remember, system is static, net external force and torque on the system is equal to zero. Now here's a question for you guys. Why don't internal forces matter? Like you might have heard of the term external and internal forces. For example, let me give an example. So if you have a block over here, and then maybe you have a massless string there, and then let's say there's an external force that's pulling that string over there. Yeah, so the external forces on this, right? You'll have a gravity downward, we'll have a normal force upwards. So those are the three external forces. We have the gravitational force, we have the force you're pulling it with, and the normal force, assuming there's no friction, right? Those are the three external forces, but there are also internal forces. So forces internal to the system. For example, if we're looking at this point over here, so the point where the rope and the mass intersect, let's call that point P. If I draw my free body diagram for the point P, what will it look like? Well, there will be a tension force to the left, which is from the rope, right? And there will also be a force from the block, right, pointing towards the left. And these are internal forces. Basically, they're action-reaction forces. You probably have heard that term before. Like for every force, there's an equal and opposite force, right? And I'm kind of giving away the example, the reason why internal forces don't matter. So can someone tell me why internal forces don't matter? Like, why do I say net external force? Why don't I say net external force and net internal force? Is there a difference? Someone want to tell me
They
that?
just cancel. They just
Yeah,
cancel it because they're all pairs.
yeah, exactly. Yeah, everyone's saying this. Yeah. Good job, everyone. So they just cancel because internal forces, they're equal and opposite. So they at the end, if you sum all the internal forces together, you'll get zero. And also, if you sum all the internal torques together, you'll also get zero. So yeah. Oh, yeah, that's actually the second question. Do internal forces create torque? Well, you guys probably can answer this question. So we'll assume that all like if you have two internal forces, right? They're force pairs. We'll assume they act at the same point. So in other words, what we're just doing is we're doing F crosses like some radius vector, and we're doing F crosses the same radius vector. That's just equal to 0, right? So internal forces create no torque. So the answer to this is no, right? Internal forces, they also, the net external force is just the same thing as saying the net external and net internal force, because the net internal force is always equal to 0. So just remember that if a system is static, net external force and torque on the system must be 0. Yeah. Do you guys have any questions on that? Nope. All right. Let's go on. All right. Let's talk about the bending moment. Some people call it that, but essentially prove that given that the net force on the system is 0, if the torque about a single point is 0, then the torque about any point is 0. Maybe I'll give you guys a minute to think about this. If you guys have an idea or you guys have an answer, message me in the chat, and like I'll tell you if it's right or wrong. It's probably right, but we'll go over this in a minute. So maybe at 22, we'll talk about it. Yeah. Oh yeah, by the way, please send it to me, not my iPad. Yeah. All right, let's go over it. Um, okay, so a lot of people, I got a few messages saying that if you know the net force on the system is 0, then you immediately know that the net torque on the system is equal to 0. And actually, that's not necessarily true. So let's take a look at it. So I'll give you guys a counter example. So if you have a rod over here, all right, and then let's say I have a force on one end, I also have a force on another end, right? These are my two forces. They're equal and opposite, but they're applied at different points, right? Now, the net force is 0 because these two are equal and opposite, but is the net torque really 0? Well, if I look at the torque about maybe this point in the center, right? The total torque, let's say this has a total length of L. the total torque will be equal to F L over 2 plus F L over 2, right? Which is FL, and that's not equal to 0. So it's actually another misconception, right? Just because you know that the net force on the system is 0, you don't know that the net torque on the system is 0. And it's not, and we're not trying to prove, like, here, what we're trying to prove is that we know the net force is 0, and we also know that the torque's about a single point, we know that the torque about a single point is 0, then torque about any point is 0. I have a question. What is the, oh wait, no. Isn't one of the torques negative? So, all right, a question about this calculation over here. All right, so let's take a more detailed look at it, right? So let's say this will be my R1 vector, right? This is my R1 vector. This is my R2 vector. My sigma of the torque should equal to like F cross R1 plus F cross R2. If you use your right-hand rule, right? Let's do it with me. So let's look at this force over here, the torque produced by it. The force is pointing upwards. The radius vector is pointing to the right. If you use your right-hand rule and you do the cross product, you'll find that the torque will point into the page. So the torque will be pointing this way. Basically, when I'm drawing a circle with an X, it shows that the direction of the torque is pointing into the page. Now, if I look at this one over here, let me use a different color. If you do it again, right? F crosses R, F is pointing downwards, R2 is pointing towards the left. You'll get torque points into the page. It still points into the page. The torque, those two torques, they don't cancel. They're mutually reinforcing. So I'm actually adding the two together. I'm doing addition, not subtraction. If we instead had, say we had a different case where here's my rod, and I have two forces like this, right? F, F, then yes, in this case, the torques produced by these two forces would indeed be 0. Because once you do the cross product, right, like FR1, this is R2. If you do the cross product, right, F points up, R1 points to the right, the torque will be pointing into the page here. So this is my torque 1. But if I do the cross product for this pair over here, right, then my F points up, my R2 points to the left. My torque will be pointing out of the page. This is my torque 2. And yes, in this case, the sigma torque would equal to FL over 2 minus FL over 2 equals to 0. But you always have to be sure that you have to be sure of the direction of the cross product, right? When we're looking at this example over here, so oops. Over here, we indeed have a non-zero torque if you check out the direction of the cross product. So it's a counterexample for, like, this is just like this, oh my God. This example over here, it's indeed a counterexample for the claim that if the net force is 0, then net torque is 0. You can't just say that, because you can have the net force is equal to 0, but your net torque doesn't necessarily have to be 0. Okay, does that make sense? Because a lot of people are saying that, and I just wanted to clear up that misconception. Anyone have any questions on that? Because it was a thing I stumbled on too, but like eventually you'll understand it. Let's try to understand now. Does everyone get that? Just because your net force is 0, your net torque does not have to be 0. Okay, everyone seems good on that. So let's go on to proving the actual theorem. So the bending moment theorem. Let me clear up the screen. By the way, if you have any questions, message me in the chat or just interrupt me, and then yeah, I'll try to answer the question. Oh. All right. Okay, so let's go on to prove. Okay, given that the net force on the system is 0, the torque about a single point is 0, then the torque about any point is 0. I remember someone had a pretty good explanation about it. AD, can you give us your explanation, your proof of it?
Okay. So basically what I did was that, like, if the torque across one point is zero, and like let's say the object is rotating or whatever, is doing whatever, it's just gonna stay however it's rotating by Newton's first law. Like for Newton's first angular law. And then by that like logic, since the state of rotation is not changing, that means if you try to take the torque about any point, you're still gonna get zero because the angular acceleration is zero.
Yeah, I like that. So you're basically using that, you're using the fact that we have torque equals moment of inertia times angular acceleration. You know that torque about some point is zero, so your angular acceleration is zero. Then the torque about any point must also be zero, because your angular acceleration would, that's no, regardless of whatever point you're looking at, whatever point you're taking the angular acceleration about. Angular acceleration, that's independent of whatever point you're taking the torque about, right? I like that explanation. And then there's another way to prove it that's more fundamental, and it will come from, instead of torque equals I times the angular acceleration, comes from torque equals like F cross R, right? That definition. And how will it work, right? So let's consider we have a body over here again, and then maybe I have, like, say this is the first point I'm taking the torque about, and then there's another point over here I'm taking the torque about. So let the original point be O, let the new point be O star, right? And then maybe let me draw a few forces on the body, right? So we might have a force over here, maybe a force over here in this direction, maybe a force over here, right? We're given that the net force is zero and the torque about a single point is zero. So let's say O is the point about which the torque is zero, right? So we know that if we're doing sigma Fi crosses Ri, that equals to zero, right? Where Ri will be from each point to the O point, right? So for example, if this is F1, this will be R1, right? And you're taking the cross product between the two to get the torque. Now, I want to prove that if you're taking say Fi and then crosses, let's say, for example, I'll say Ri star. I want to prove that equals zero, where I'll say Ri star, I define that as the radius vector from the point we're taking the force from the point the force is acting to the new point I'm taking the torque about. So like an arbitrary O star, right? So how can I also rewrite this? I basically want to prove this, right? So how do I prove that? Well, this is R1 star, right? And notice that there's a constant vector between O and O star that I'll call, let's say, O star, right? That vector. So Ri star, that equals to Ri, oh wait, these are vectors, plus O star vector, right? And O star, that's a constant vector, but Ri star and Ri, it's like it changes from each point, right? Like this point over here and that point over there, they have different R vectors, right? So then I can I can rewrite this equation, right? Let me use a different color for you guys to see better. That's equal to Fi crosses Ri plus O star, right? What does that equal to? Well, that equals to, because you know that cross products are distributive. So Fi crosses Ri plus sigma Fi, and because O star is a constant vector, I can pull that out and it's just cross O star, right? Now look over here. So I already know I'm given that the sigma Fi cross Ri that's equal to 0. So that's just 0, right? And I'm also given that the net force on the system is 0. So sigma Fi is also equal to 0. So that also cancels. And look, we also get 0. So basically, what is the result of our proof? Well, the result is that if you know that like the net force on the system is 0, and the torque about, and you found a point about which the torque is equal to 0, right? Then you know that the torque about any other point in space is also equal to 0. And what's the benefit of this? Well, that means that if we have a situation that's like it's a static situation, then we can choose whatever point we're taking the torque about and we set it equal to 0, because we know that in this static situation, it doesn't matter which point we're taking the torque about, like the fixed point we're taking the torque about, the torque about that point will always equal to 0, right? I know that was a mouthful, and that was like a big proof, like with a lot of vector algebra. So does anyone have any questions about that? There probably will be, and I'll do my best to answer them. And I welcome all questions, by the way. And if anything didn't make sense, or you guys want me to repeat anything or clarify some part of the proof, let me know. All right, there's something in the chat. Why are the points outside of the object? Good question. Well, I think you're referring to like the point we're taking the torque about, right? Is that correct? Yeah, okay. Well, the thing is, we can take like there's no restriction for what point we're taking the torque about. You can take the torque about any point in space, right? You could take the torque about the center of mass, which might be over there. You could take it about like a point over here, right? You could take it about any point in space. No one tells you that you have to take the torque about a point inside the body. Usually, I mean, I know that usually you might see that like we're taking the torque about the center of mass, and a lot of times we'll be doing that. But in reality, you can actually take the torque about any point in space. And yeah, there's really no restriction about what point we're taking the torque about. Does that make sense?
But that's only for static system, right?
Yeah, so for static system, if we're taking the torque about any point, it would equal to 0. Yeah. Any other observations? Oh, given the freedom to take the torque about any point, should we use the center of mass? This is a great question. And the answer boils down to it depends on it basically depends. So a lot of times, right, we're probably like a lot of times in static situations, we might be solving for like a force, or we might be solving for an angle, right? We do have the freedom to take the torque about any point, and then we really want to exploit it. So sometimes we'll take it about the center of mass. Actually, in the next example, I'll show you guys an example where we're gonna choose a good point to take the torque about, and it's gonna be a really convenient point, and it will let us like it will let us have a simple solution. So yeah, given the freedom to take the torque about any point, sometimes we'll use the center of mass, sometimes we'll use like a different point. It really depends on the situation. All right. Another
One
question.
thing,
What's up?
yeah. So wait, so the cross product is distributed, right? So how do we get that the force times the OO star is 0? Is it just because the force is 0, or?
Yeah. So like I pulled it out, so we have let me show you. So we have this over here, right? So
Yeah.
it's just sigma F cross the OO star vector, right? We are given that
Mm-hmm.
net force on the system is equal to 0. So we know that sigma Fi, that this thing over here, it's equal to 0. And if you're doing 0 crosses any vector, it equals to 0, right? That lets us also cancel
Oh,
that part off. Yeah,
yeah.
good question. I
Okay.
like how you're checking the calculational details. Yeah. I think there's another question in the chat. Um, if okay, you can take the torque about any point if you apply a force that may cause a torque about one point, but doesn't cause torque about another point. If you choose that other point, in reality, the object rotates. Why does it produce no torque about that particular point where the torque is zero? All right, let me see. All right, good question, good question. Let me, how about I'll clear the screen over here and I'll try to answer that. So, which part should I clear? All right, I'll clear this part. Right, basically what the question is saying is that, okay, let's go back to the example with our that rod, right? So we have a rod over here. So our rod, okay, and then maybe I have a force over here, and I have a force over here, right? Therefore zero. All right, and then if I'm taking the force about like the center over here, or sorry, if I'm taking the torque about the center over here, we'll get a non-zero torque, right? Intuitively, it makes sense because in this setup, the stick will start rotating, right? Now the question is, if we're instead taking the point about taking the torque about this point over here, the problem is when this force over here, it produces no torque, right? Thing is, there are also other forces in the system you have to consider. This force over here, it will also produce a torque, and the torque will be equal to F times this is L, whatever length it is, right? So, object, yeah. So, yes, it is true that this force over here does not produce any torque about like this new point over here, right? But the thing is, now that we're taking the torque about this point, the torque due to the force on the left, it changes, it becomes bigger, right? And that is able to like that increases just right so that it's actually you'll find it's equal to the original amount of torque. Does that make sense?
But actually, I had like an add-on to that.
Yeah.
Since you can take any point, if you take like the specific point where all the forces produce no torque about that particular point.
Yep.
But I mean, in this scenario, like if there's some point in this scenario where there's no like torque at all, and the object still rotates because that's how it works in reality. How did that make sense?
Oh, well, if you find, well, okay, well, we just proved that, if you, well, like we proved mathematically that in that case, if you find a point at which the torque is equal to zero, and you know that the net force is equal to zero, then the torque about another point would have to equal to zero. So I think, basically to answer your question, that is indeed true. It is possible for, like for example, I have a case not necessarily static where the torque about one point is equal to zero, but the torque about another point would not be equal to zero. But that would only happen if the system is not under force balance. Because if we go back to our mathematical equation over here, right? We got, let me rewrite it. So essentially what we got is that we have sigma Fi cross Ri and then plus, plus the sigma Fi and then cross the OO star vector, right? Okay, now we are given that this is, so going back to what you said, right? We're given the condition that the torque about a single point would be equal to zero. So we know for sure that this is equal to zero. In your case, the only way that the torque about one point would be equal to zero, while the torque about another point would not be equal to zero, would be if if the sigma Fi is not equal to zero. So in other words, you don't have net forces equal to zero. In that case, we don't actually we don't have that the torque everywhere is equal to zero. Because remember, when we were proving this, we were assuming that the net force on the system was equal to zero. If we don't assume that, then we do not necessarily know that if the torque about a single point is zero, then the torque about any point is zero. Does that make more sense?
So does that mean if the forces aren't balanced,
Yeah,
one point could say it's rotating and one point could say it's not?
yeah. So if forces are not balanced, then maybe about one point we'd say that there's angular acceleration, but about another point there's no angular acceleration. It's actually pretty cool, but yeah, that's how it works.
Oh,
It's
okay.
pretty interesting. Yeah. I'm glad you asked this question. It's a really good question because it really lets us go back to the details and the assumptions of this. So remember that when we're applying this bending moment idea, we're always assuming that the net force on the system is equal to zero. That's how we're able to cancel out this term and say that the torque about any point is equal to zero. Yeah, really good question, by the way. Any other questions before we move on? All right, if not, okay, then let's go on. All right, let's move on to some problems and some tricks, all right? All right, so what's the overall technique for static problems? Okay, oftentimes the problem will ask you for the condition for the system to be static. First thing you want to do is draw a good free body diagram of the system you're looking at. Uh, there might be forces needed to solve for, think of them as variables. If you can easily balance two forces, do that first and write enough force balance and torque balance equations to solve for the variable. You can read this, but like basically, you don't have to memorize this. You'll acquire it through technique. So that's why I'm going through it so fast. Once we start this next problem, you'll get a better idea, right? Okay, so just a few tricks. Use your intuition. Don't solve for every force, do some sanity checks, all right? Yeah, helpful to take torque about a point that many forces act upon. But basically, these are just techniques and don't memorize these, right? Once we do the next problem, you'll get a better idea and you'll acquire like a better intuition when you're doing more stacks problems. Okay, so let's do this one together since it's probably like the first problem we're doing together, right? Right, a ladder leans against a frictionless wall. If the coefficient of friction with the ground is mu, what is the smallest angle the ladder can make with the ground and not slip? All right, let's draw a picture and a good free body diagram, okay? That's our wall and that's the ground. Let's say that is the ladder. What's the smallest angle the ladder can make with the ground? So let's call this angle here theta. Let's say we're given that there's friction with the ground, right? So we're given mu, we're given the mass of the ladder, we're given the length of the ladder. So remember the length of the ladder is L, right? All right. So let's draw a free body diagram. How about someone tell me what the forces on the rod will be?
Friction, normal, and gravity.
Friction, normal, gravity. Good job. Yeah. All right, friction, normal, gravity. All right. Yeah, gravity would be over here. Mg, normal force over here. Let's say that point is 0.1. This point is 0.2. So this will be N1. Let's call it N1. Now there's a friction. Oh, let me use a different color, guys. All right. Now, okay, someone tell me what direction will the friction force be at 0.1? Use your intuition here.
Up, left.
Yeah, to the left. And the reason is because the ladder, if you think about it, the ladder wants to slip so that it's this way, right? So it will slip like that, right? And the friction force tries to counteract the relative motion between the stick and the ground, right? So we'll expect the friction force um at at when it's at the smallest angle, the friction force will be pointing towards the left. So that would be, let's say, friction. And by the way, we're given that there's only friction with the ground, there's no friction with the wall, so that simplifies it a lot, right? So this will be our N2. All right, what can we do first, right? Obviously, we're given it's a static situation, so we want to balance forces and torques. But let's look at the free body diagram first, right? There are probably some forces we can like easily equate, right? So for example, we have a gravity force here and we have a normal force here. And those are the only directions in the only forces in the vertical direction. So they must be equal, right? So let's say, I'll call, instead of writing N1, I know that N1 equals mg, right? For there to be force balance in the vertical direction. So this force over here, its magnitude is mg. And I also know that the friction force, right? We know F is like mu n, right? Oh, mu n. So instead of writing F, I'll replace that with mu n. Well, mu n, that just equals to mu mg, right? Because we just found the normal force equals mg. Oh, sorry. Mu mg. So I can erase this and say it's, oh, right, mu mg. And now, if we balance forces in the horizontal direction, I know N2 equals mu mg. So I can replace N2 with mu mg. This simplifies it a lot, right? Now, what do we want to do now? So we want a convenient point we take the torques about, right? The best way, right? We want to take torque about a point that has the fewest forces possible. Sorry, that has the most forces possible. And the reason is because, for example, if we're taking the torque about, let's say I take the torque about this point over here, right? Then I'll have to consider the torque due to the gravity, due to the normal force, and due to the friction force, right? Those are three forces, okay? Now, if I do the torque instead about this point over here, I only need to consider the torque due to that normal force and that gravitational force, right? Let me see. There are some questions in the chat. Yeah, N1 is not equal to N2, by the way. Yeah, we just have, sorry, I should have written it better. So remember, our equations were N1 equals to mg, and F1 is equal to N2. Yeah, and we also had F1 is equal to mu N1. So once you solve all that, you can get everything in terms of mg. Yeah. Don't worry about it. It's good that you're checking all the calculational details. Okay, so let's keep going. I'll erase this for now, just to because we're running out of space on our board. Oh shoot. Sorry, I think I closed my iPad or something. Let me restart the sharing. All right, you guys can see that
Wait,
now. All
did
right.
we choose the maximum value of the frictional force so that we could minimize the angle the most?
Yeah, that's very good, very good. Yeah, so the friction force, remember, yeah, I didn't mention that, but it's good you're mentioning that. So we want F1. We know that F1 will always be it's always less than or equal to the mu max and then times like normal force 1, right? So yeah, very good, very good. At the minimal, like think about it intuitively. At the minimal angle with the ground, it's when it wants to slip the most, right? So the friction force has to be the greatest, because if it wants to slip the most, you want the greatest force to counteract it so that it stays static, right? So in this case, F1 max would equal to mu max and then times N1. Very good. So yeah, in this case, our friction force will be equal to mu max times the mg. And then now we want to balance torques, right? So we want to take the torque about this point over here. We want to take the torque about 0.1 because it's the most convenient. Of course, you could also take the torque about this point and set it equal to 0. It's the same thing. You just get like, it's just a bit like it's a bigger algebraic equation and it's easier to make a mistake. The best idea would be take torque about 0.1. If we do that, what happens? Well, the torque about 0.1, let's first look at the torque due to that force over there. So the normal force acting at 0.2, the torque due to that would be mu mg, and then times, remember, we want the perpendicular component. We want that component, right? That should be the sine theta, because we know this is also theta. So sine theta, by the way, when I write s theta, it just means sine theta. It's just shorthand, right? And then times L. And then notice that's creates an opposite torque to the gravity, right? So it should equal to mg times cosine theta. So let's write cosine, sine, cosine theta, and then times L over 2. Now if I cancel mg, I cancel the L, what do I get? I get tan theta equals to 1 over 2 mu. So this will be the minimum theta. This is the minimal theta, and then this is the maximum mu. So we solved the problem. This the angle, the smallest angle the ladder can make with the ground and not slip satisfies that tan of that theta is 1 over 2 mu max. Now, how about I ask a follow-up question? Or first, okay, first, does anyone have any questions about this?
Wait, why do you label the coefficient max?
Oh, yeah. So remember that friction force, right? This is static. This is a static situation, right? Remember, if you have static friction, your friction force is always less than or equal to the maximum mu times the normal force. Remember that?
I thought the maximum was just mu n.
Or yeah, you can call that mu. It's just, yeah, sure. Just we can call that mu. Yeah, it's the same thing. But like, yeah, the friction
Oh, okay.
force. Yeah. Yeah, I get what you're saying. I get what you're saying. Yeah. So it's always less than or equal to mu n. Um, yeah, so I guess we can erase that. But yeah, the friction force in a static situation, it's less than or equal to like the maximum static friction times the normal force, right? And then from that, we're getting like this will be the condition for the minimal angle with the ground. Now, oh yeah, any other questions? Or if not, then let me ask you a follow-up question. What if I wanted to ask you for what's the I don't want to find the minimal angle with the ground. I just want to find the condition for the angle with the ground so that the stick does not slip. If I maybe you guys didn't catch that, but we found that tan theta, the minimal theta with the ground, right? That satisfies tan of that theta is 1 over 2 mu. Now, what if I wanted to find what's the condition for theta such that the stick does not slip? So would it be tan of theta is less than or equal to, or would it be greater than or equal to 1 over 2 mu? Let's use our intuition. And anyone have an answer? Yeah, greater than or equal to. And why is that? Well, because the smaller the angle with the ground, the more likely it's going to slip. You can think of it intuitively, right? You've probably tried this before. Maybe like you can think of it intuitively in your mind, right? A smaller angle with the ground, it's more likely to slip. So if your theta is greater than the minimum theta, well then yeah, like it's not gonna slip, right? That makes sense. And tan theta increases as your theta increases. So it's just basically a piece of algebra that you get the condition for theta must be that tan theta is greater than or equal to 1 over 2 mu. Yeah. Anyone have any questions on that?
Yeah, like I get intuitively why like the smaller the angle, the more it'll slip. But is there like a actual physical reason why that's the case? I was
Yeah.
thinking it was something to do with the torque, but I'm I have no clue.
No, that's good. So if we look back over here, right? Let's say, this equation over here, which was balancing the torques, right? The thing that makes, well, basically the force or the torque that makes the ladder slip, right? That's due to gravity, right? It's gravity that's making the ladder slip, right? And if we look at this over here, the torque due to gravity, that's mg cosine theta L over 2, right? The smaller the angle with the ground, the greater cosine theta is, right? And the greater cosine theta is, you need a greater mu to be able to balance the torque due to the gravity, right? So yes, if you have like, this is the algebraic explanation that's like, it's like you have the intuitive explanation, and this is the algebraic explanation. It's because your cosine theta, it increases as theta decreases. So as the theta with the ground, as the angle with the ground decreases, there's a greater torque created by gravity that needs to be balanced by the friction force. Does that make sense? I like how you're asking for the algebraic way.
Yeah, that made sense.
Yeah, I like those questions. Any other questions? Let me see. All right, I don't think there are any other questions, so let's go on. Oh, we're running low on time. That's not good. All right. Here's an idea. If forces are applied to 3 points in a static system, then the extensions of the vectors representing the net force at each of the 3 points must be concurrent or parallel. And we want a proof for this. For the sake of time, I'll just go over the proof. So essentially, what are we saying, right? If we have a static system, for example, have this, and then maybe this is one force, and then we might have another force over here, and then yeah, okay, we have another force maybe pointing in this direction, like this. Now, what is saying is that if I draw the extensions of all these forces, actually, we're first given that there's force balance, right? So these 3 forces, if I do their vector sum, they equal to 0. Now, what the theorem is saying is that if I draw the extensions of each of these vectors, right? Extend this, I extend this, they must all meet at one point for there to be torque balance, basically. And why is that so? Well, okay, we're given that sigma f equals 0, right? And then we know that it's a static system, so sigma tau is also equal to 0. Well, remember when we proved that sigma f was equal to 0 and sigma tau was equal to 0, basically when it was a static situation, it doesn't matter which point you're taking the torque about, the torque about that point has to be equal to 0. And then if these 3 vectors or the extensions of these vectors, they all meet at this one point over here, let me draw that in blue. Notice that the torque about that point has to be 0. And why is that so? Well, remember, torque equals to force cross r, right? Your force here, they're in the direction of r, right? They're just scaled versions of the radius vector, right? Because the radius vector of, if this is f1, right? This is f1 vector, then the r1 vector would be over here. It will be in this direction. This is f2, and this is R2, right? And so on for R3, F3 and R3, right? Remember, here we're doing the cross product between parallel vectors, right? F and R are parallel here. And if you're doing the cross product between any two parallel vectors, it's always equal to 0. If you remember back in the like vector cross product days, right? It's equal to 0. So then this will equal to 0. And we know that they're concurrent, right? If they're concurrent, it's equal to the torque will equal to 0. And because we know that the torque about that point is equal to 0, since we also have force balance, then the torque about any point must also equal to 0. And then you might ask, right? Concurrent or parallel. Why do I say parallel? Well, essentially parallel, it just means that the lines are concurrent at infinity. For example, if I have this scenario where I have three forces over here, maybe looks something like this. Those are my three forces. Indeed, if you look at it, we have both force balance, like we have force balance and we also have torque balance. Assuming that these two, say this is F over 2, this is also F over 2, right? So what is this telling us? Basically this theorem just tells us that if you have a static system, then if you extend the vectors of all the forces, they must meet at the same point or they must be parallel. That's essentially what it's just saying. Does that make sense to everyone? Any questions about this? All right, okay, let's move on then. All right. Actually, I'll let you guys think about this for homework. First, basically, just if we have forces acting at 2 points, what can we conclude? And also, if we have forces acting on more than 3 points, must the extensions of the net force vectors be concurrent or parallel? All right, think about that for homework. But let's go back to this problem, and we'll solve it using the previous idea, which is just this. All right. Let me draw the diagram again. And if anyone has an idea on how to do this problem, like you're welcome to tell me, and then you can like lead the way, you know. So these are our forces, remember? We found that this was gravity, right? This is normal force. And after a bit of doing the force balance, right? Oh shoot, let me draw this a bit more accurately. So this will be the normal force. This is gravity force. This is normal force. This is friction. So we got this was mg. This was also mg. This is mu mg, and this is also mu mg. How do we use the idea that there are forces applied to 3 points, right? Here we have 3 points where the forces are applied. 1 point here, 1 point here, 1 point here. If we have these 3 points where forces are applied to, we know that the extensions of the vectors representing the net force at each of the 3 points must be concurrent or parallel. So what is this saying? We're saying that if we draw this extension, draw this extension, and then I'm looking at the net force at this point. So I do the sum of the friction force and the normal force. They should all meet up at this one point over here. How do I use that to solve for the minimal of theta over here? Anyone have any ideas? Give you guys maybe a minute to think about it. All right, I'll go over it for the sake of time, but all right, we're given that these 3 lines here, right? So this one, this one, this one, they all intersect at the same point. They all intersect over here, right? Well, obviously, this line and this line, they definitely have to intersect because like those two, they definitely intersect, right? We'll say it's over there. For this line over here, this one to intersect with those two, this has to be a right triangle. Well, that has to be a triangle, right? With a vertex of that point. And then if I draw it maybe wait, so this has to be a triangle, right? That's a triangle. Notice first that if I'm looking at okay, how about let's say this. So looking at this triangle over here, so maybe this triangle, the green triangle I have, and the purple triangle, you know they're similar, right? This is a bit of geometry. You know they're similar. So if they're similar, they have the same angles, right? So this side corresponds to this side, right? And then this side corresponds to that side, right? So if the angles are the same, then I know that, okay, if I'm dividing this length by this length, which is mg divided by mu mg, it should be equal to if I'm dividing this length by this length, right? Which will be, if I do the algebra, right? This should be L cosine theta, L sine theta. So it should be equal to L sine theta and then divided by this length, right? What's that length? That's L cosine. Wait, hold on. Yeah,
L/2, right?
yeah, L over 2. Yeah, nice catch. Yeah. L over 2 cosine theta, which is like 2 tan theta equals to 1 over mu, and we're getting the same result. Tan theta equals to 1 over 2 mu, right? Isn't that pretty cool? So we can solve the problem without having to write a torque equation. We're just doing geometry here. We just found the similar triangles and we found that, like, we proved that like those, like that has to be concurrent, right? They have to meet at that point. So this must be true. And then you'll end up with tan theta equals 1 over 2 mu as before, right? Any questions about that? Not that, if you're not really good at the geometry, that's fine, because this is physics, but make sure you have a good idea of what's going on. Any questions about that? Oh, let me see. Just to clarify, what is L? Oh, L is just the length of it's the length of the ladder. So I'm saying that this length over here, this is the ladder, right? The length of the ladder must be L. Yeah. Here's another question. Oh, okay. For practicing, is the competitive physics book you sent good? Yeah, it's pretty good. All right. Okay, next slide then, I guess. Think about this following problem. Maybe it will be for homework. A ladder, so it's the same problem essentially, except this time, okay, you still have the normal force, the friction force, gravity force here, and you have the normal force here, N2. But what happens if you also have oh shoot, let's say, oh wait, I'll have to rename this. So this is N2, this is friction 2. This time I also have friction with the wall. So remember last time we didn't have this friction force over here, but this time we have to, like we're saying, there is the rough wall does have friction. Before we said the rough wall didn't have friction, it was only the ground, right? Now the rough wall also has friction. How do you solve this problem? I'll probably give it to you guys as homework, but think about this. It's pretty interesting. You can solve it using the previous idea that the forces have to be concurrent. We'll skip over that problem for now. Let's talk a bit about massless strings and ropes. Main assumptions: assume the string or rope is massless, string cannot stretch or compress. Tension must always point along the direction of the string or rope. And why is this so? Well, you know that the string is massless, so if we consider it as like many infinitesimal segments, right? It looks something like this. If I'm looking at this one over here, right? It will have a tension this way, tension that way, right? If wait, first off, it's masses, right? So we know it has to be under force balance because you know F equals ma, right? first of all, it's static, so the force has to be equal to 0. And even if it wasn't static, like if the rope was accelerating, your net force still has to be equal to 0. And why? It's because your mass is equal to 0. If your force is not equal to 0, if your force is equal to 0, we're saying 0 equals 0 times acceleration. We're saying like basically force equals 0 times acceleration. Your force is not equal to 0, then your acceleration will be infinity, right? So if you have a force acting on a massless object, you'll have an infinite acceleration, which cannot happen, right? So basically, your the segments on the rope has to be under force balance. Now, why must the tension always point along the direction of the string or rope? Well, that's because let's go back to this drawing over here. This one. If I had, for example, the tension pointed this way, first off, for there to be force balance, the tension would on that side would have to be this way, right? But that would necessarily mean that the tension will point that way on the other one, right? Which is not possible because we know that these two forces must be action and reaction pairs, right? They must be force pairs. They must be equal and opposite. If the tension was not pointing along the direction of the rope, these two would not be force pairs, which violates like physical laws, right? So we know that tension must always point along the direction of the string or rope. For basically the tension must always point along the direction of the rope. Yeah. Those are just some assumptions. Let's go on to this problem. Massless rope is wrapped around a rough pulley with a coefficient of sag friction mu. Segment of rope is in contact with the pulley subtends an angle of phi. If one end of the rope is vertically attached to a weight of mass m, what's the minimum force F that has to be exerted at the other end for the rope and the mass to remain static? Wait, we're actually we're basically out of time now, so I'll just do hold on. Sorry. All right, how about let's go back to the previous one because there's a question on it. And then maybe I'll give you guys this problem for homework because we're basically out of time. How did you know these? Wait, the question is, how do we know the purple triangle and the green triangle are similar? Well, the answer is that, basically, we drew this line over here. The line over here, it has the same slope as this line over here. Well, it's negative, right? So let me draw a better diagram. So we have mu mg over here. We have mg over here, right? And then we want to prove that this one over here is similar to this one over here, right? Well, basically, it's just that you know that we said that this, right? That this angle over here, it's a bit hard to draw. So this angle must equal to this angle should equal to this angle, right? And then you also know that this angle, those are both right triangles, right? So they're both right triangles. So we know two of the angles are equal. We know the third angle must also be equal, right? And that's just AAA similarity, right? Does that make sense? All right, yeah. But anyways, if we go back to the problem over here, let me just draw a quick diagram for you guys and you can think about it. We have a rough pulley and then you have a massless rope wrapped around it. So it looks like this. Okay, the pulley has a coefficient sag friction mu. Let's say this angle over here is phi, right? That's phi. And then one end of the rope has a mass with weight m. What's the minimum force F that has to be over there? So how would I do this problem? Well, you know that this is like this force over here is mg. So the tension over here tension at this point, the T would equal to mg, right? Now, if I examine an infinitesimal angle of the pulley, right? So let's say this is some d theta. I have a tension over here. I also have a tension over here. But there's also going to be a frictional force, right? So there will be a frictional force in, let's say, maybe in this direction. There'll be some frictional force, and then you want to find this frictional force, and you want to find like this will be T prime, right? You want to balance T prime, T, and F. Yeah, basically you want to find T prime given your T and your F, right? That's basically how you solve this problem. Okay. Yeah, so that's how you solve the problem. I'll let you guys think about it for homework, but
Why
Huh?
why the friction force is in the same sense that the tension?
Oh, why is friction force in the same direction as tension? Good question. So, actually, yeah, so we can say that basically, so we know normal force is in this direction, right? This is our normal force. And then yeah, so if that's your normal force, wait, that's a very good question. So let me erase some stuff. All right, so let's draw the forces a bit better. So you have a tension force here, another tension force here, right? And then because they all have an inward component, actually it will be, that's your normal force. It's probably not going to be that big. So this is your normal force, right? Actually you're right. So the friction force, it would point yeah, it will point in the horizontal direction, I think. So that way, that's your friction force. And then well, really, it actually doesn't matter which direction you're writing it, because like basically F, if I'm looking at the projection onto the direction of the rope direction, right? That'll be like, for example, if I drew my friction force as this, you're right, I actually be wrong. So yeah, you're right. I should have drawn it a bit better. So it would be in the horizontal direction. That would be what F will be, right? Yeah, good correction. F would be, yeah, F would be in the horizontal direction. Yeah. Wait, good catch. All right. Let me see. Yeah. So F should be in the horizontal direction. Yeah. But you guys can think about this for homework. I'll just go over the next idea.
Oh, sorry.
What's up?
I was gonna ask a question on the last.
Oh yeah, what's up?
Oh, wouldn't the F help, help pull it up so you can minimize the force you're bringing down with?
Oh, yeah. Well, yeah. Sorry. Yeah. F should be towards the right. Yeah. Oh, yeah, that's my bad.
Okay.
Yeah. So F points towards the right. Yeah, if we're looking at it this way, then yeah, F would point towards the right. So the tension would be decreasing. Yeah. Okay. All right, let's just quickly go over the next idea, and then I'll let you guys think about this other problem, and then I'll let you guys go, because we're like basically going over now. But when you're choosing a system, keep a clear picture of the internal forces and the external forces on the system. Balance the external forces and torques only. So here's an example. Over here, a rope rests on two platforms that are both inclined at an angle theta. Rope has a uniform mass density. So here we have a massive rope. It's not massless, right? And the coefficient of friction between it and the platforms is what the system has left-right symmetry was the largest possible fraction of the rope that does not touch the platforms. What angle theta allows this maximum fraction? Well, for for example, let me give you an example. So let's redraw it. So my rope, which I'll draw in red, will be like this, right? So if I choose my system to be like it's a box stat, so my system only is composed of the part of the rope that is not on the platforms, right? So basically be this section, it'll be a section of the rope that looks like this, right? Then if I'm looking at the external forces on this, right? Only external forces will be gravity force, but that gravity force will not be the entire gravitational force on the rope, right? It'll only be due to the mass of this portion of the rope. So it's equal to m of the like it won't be equal to m total, right? It will just be the m of this section and then times the g, right? And then the other two forces, can someone tell me what are the other forces on this system? If I'm choosing my system to be the rope, the portion of the rope that's not on the platform.
The normal forces?
Well, there's actually no,
Tension.
yeah, it's tension. There's actually no normal force because this part of the rope is not on the platform. But yeah, there will be two tension forces that will be pointing, they're pointing along the rope, right? So in this direction, so tension and tension, right? I know this makes an angle theta, so I know like 2t sine theta must be equal to mg, right? Or like, let's say, uh, yeah, mg, where m is the portion of the rope. It's the mass of the portion of rope that's not on the platform. And then, for example, let me ask you, if I chose this to be my system, like the portion on the right side, sorry, like the part of the rope that is on the platform, but only like the part on the right side, right? So it looks something like this, right? Or maybe not that slope. So something like that. Then can someone tell me what are the external forces on this system?
It would be like gravity, friction, and normal
Yeah, gravity, friction, normal, and there's also a tension force. So like
tension. Yeah,
yeah,
at the
and
end, right?
yeah, and then you have a tension force this way, and then you'd expect the friction to point towards the right, right? To balance the tension force and the component of the gravity force. So there will be a friction force over here. And to solve this problem, right, this m, by the way, this is the m on the platform. It's not equal to this m over here. So this problem, which I'll give you guys for homework, basically the idea, the the thing to take away about this is just to choose like different systems and you can solve for different variables, right? And choose your systems wisely. And eventually you'll be able to solve the angle theta that allows the maximum fraction. Yeah, any questions about that?
Wait, one like question in general. When you solve like problems out of this book, would
Mhm.
you do you like if you get stuck, like do you look at the solutions or like just
Uh,
keep
I
like
take a
grinding?
peek. Yeah, take a peek at the solution and then try to work on it a bit more. And then if you're really, really stuck, like if you spend 2 hours on the problem and you're still stuck, just look at the solution, I think.
Mm.
All right, we're basically out of time now because the next class is starting. So, any last questions, or anything you want to go over?
Will this presentation be shared in the Discord?
Yeah, basically I'll send an email to everyone and then you guys can get it. So, uh, hopefully everyone's on the email list and then I'll just send it to like by email. Also, I'll reply to,
Okay.
yeah, go ahead.
Oh yeah, no, sorry. I just said okay, thank you.
Yeah, no worries. All right, any last questions?
And when is the next class?
Oh yeah, next class is next week at the same time as as like today.
Okay.
All right. Then I'll see you guys next class. Make sure to take a look at the homework, and then yeah, thank you guys for coming.
Thanks, Lucas.
Yeah,
Thanks to you.
Yeah, thank you
thank
for
you.
your insight and teaching.
Oh.
Thank you.
Sorry, I just had a question. I thought it starts from 7:30 PDT, not EST. I was kind of confused.
Oh wait, which class?
Isn't this physical chemistry?
Oh, physical chemistry starts now, I think. I'm not teaching it.
Oh, that's not a class? My bad.
Yeah.
What class?
Oh, this was advanced mechanics just now.
Oh, sorry. My bad.
Yeah. Wait. Oh.